Okay, exercise number 3. Here are the 3 different labelings of the vertices of a square. Different meaning that there is no symmetry of the square that transforms one labeling into the other. Why? For example, here 1 and 4 stay fixed, but only 2 and 3 swap places. This is clearly not possible by using any symmetry of the square, having 2 fixed points and only 2 here, 2 vertices changing. And here, for example, only 1 is fixed. This is also not possible. Any rotation wouldn't leave 1 fixed, so it must be the reflection about this axis here. But then here 3 would also stay fixed. So those are really different labelings, and for all 3 of them I can write down the rotation by 90 degrees and the reflection about this axis here between 1 and 4. Be careful here, 1 and 4 doesn't mean the number 4, but the vertex lying next to 1 counterclockwise. Clockwise, sorry. So in this case it is called 4, but here it is 2, but the axis stays the same here. Alright, so in this order this is the square as we are used to it. I have the 4 cycle 1, 2, 3, 4, and the reflection is 1, 4 and 2, 3 get interchanged. Here in purple, R2 is 1, 3, 2, 4, corresponding to this labeling, and the reflection is 1, 4 and again 2, 3. So the reflections are the same, at least the numbers are the same. And here R3 is 1, 3, 4, 2, and the reflection is 1, 2 and 3, 4. And now for all 3 labelings I can write down the symmetry group as a subgroup of S4. Here in the first case, I take the subgroup generated by R1, S1. And we already know it consists of these elements, R to the K, one of the numbers from 0 to 3, because N is 4, and L simply 0 or 1. So I wrote them down here by cycle structure, and that you see what you have to calculate to find these elements. Here in yellow above the elements are these expressions here. Of course, the identity is R, I simply say R instead of R1, R to the 0, S to the 0. This here, 1, 3 is R to the 3rd power times S. This here is simply RS. This is R squared S. Which consists of 2 transpositions. This here is R1 squared. At first glance it looks like a reflection, but it is not. It is rotation by 180 degrees. And this also has order 2. So you have to be very careful. It's wrong to say that if an element here has order 2, then it's a reflection. Not true. This here is a rotation. And think about it, what this here does. If I rotate by 180 degrees, exactly those here switch places, but it is no reflection. Then this here is simply S1, this is R1, and the last one is R to the 3rd power. So here all the 8 different elements written down explicitly. So I have found one subgroup of S4 of order 8. Now the same for this labeling of the vertices gives me actually a different subgroup. Just compare them. They have different elements. So I have found a second subgroup of S4 of order 8. I'm not going to tell you all the powers that I wrote down here. You should do this for yourself if you feel the need to do some actual calculations with permutations. And here in orange, D4 for the 3rd labeling, we get this here, which is yet another different subgroup of S4 of order 8. Later when we talk about the Sylow theorems, we will find out that those are the only one. There can be no more than 3 subgroups of S4. Alright, that's it. Nothing too difficult, bit tedious if you did this on your own, but I think it's interesting to explicitly see how three different subgroups of S4 of order 8 can arise as basically the same object, the symmetry group of a square, but in different labelings. Okay, and finally exercise number 4. I had to take off my sweater because I'm too worked up. So we have to show that the so-called center of a group, which consists of all the elements that commute with all the other elements in the group, is a subgroup of any given group G. The symbol Z comes from the German word Zentrum, and I found this in the English literature as well. Sometimes maybe C of G, but I'm using the German notation Z of G. So to use the subgroup criterion, I must first of all check if I'm not talking about the empty set. Now clearly the identity is element of the center because it commutes by definition with all the other elements because it doesn't change them. Okay, now we're using the condensed subgroup criterion. We take two elements of the center and then we have to show that G times H inverse again is an element of the center, and then we know that the center is a subgroup. So we take an arbitrary element of the group and we have to show that this here commutes. So we start with X GH inverse and have to end up with GH inverse X. Now, first of all, G is in the center, so I can change the places of G and X. And then I can also change the places of X and H inverse. But this is not clear yet. We only know that H is in the center, so we know that XH is HX, but if I multiply with H inverse from the left, I end up with this here. H inverse and H cancel on this side, and now I multiply from the right with H inverse. So this shows directly that if an element is in the center, then also its inverse is in the center, because this here is true for arbitrary X. So from this follows that, meaning exactly that H inverse also commutes, and this already finishes the proof. So we showed that the center is always a subgroup of any group. And of course, if the group is abelian, then the center simply is the group itself, because all the elements commute with each other. So in this case, it's trivially a subgroup because it is the whole group. So for the solution to be perfect or better, you should write down here, this implies that GH inverse lies in the center because X was arbitrary. And you should start with, I'm using the condensed subgroup criterion, and then the proof would be fine. Okay, second part of the last exercise of problem set 9. We are supposed to find the center of the dihedral group of degree n. And as hinted in the exercise, we must distinguish the cases where n is even or where n is odd. Okay. And of course, we're using this representation of all the elements of Dn and these commutation relations. So let's start with the odd case, and let's take any rotation, so r to the power of k. And to lie in the center, this here, of course, trivially r to the k and r to the l commute, because this is r to the k plus l, so I can switch or change positions of the l and the k. So all the rotations commute. But that is not enough. We also need the rotation to commute with the, or at least the s itself, and then also the generalized element r to the l s. So let's find out if this can be the case, that r to the k is the same as that. From the commutation relation we know that, or let's write it here, that this here s r to the k is r to the minus k s. So now by the cancellation rule that holds in any group, I can cancel the s simply multiplying by s inverse, which is s itself. So this would mean that r to the k must be r to the minus k. And of course I can go in the other direction also by multiplying with s. Now multiplying with r to the k gives me r to the k plus k, or r to the 2k must be the identity. Okay, now on the last problem set there was a very important fact that was given as a hint. And this leads us to order of r, which is n, must be a divisor of 2k, since r to the 2k is the identity. This is the key here. But k runs through the numbers from 0 to n minus 1, so 2k runs from the numbers from 0 to 2 times n minus 1. So we only are left with two possibilities, because here only 0 and n in this set are multiples of n. So first case is 2k is 0, or 2k is n. Both lead to a contradiction, because first of all we assumed that k is greater than 0, so sorry, I should have said here then 2k runs from 2 to 2 times n minus 1. Okay, now to exclude the trivial case r to the 0, which is the identity, I take k running from 1 to n minus 1, so 2k lies in the numbers between 2 and 2 times n minus 1. The only multiple of n in these numbers is n itself, 1 times n. So this leaves us with 2k is 1 times n, because there is no other multiple of n in here. The next one would be 2n, but this is not in the set. But this clearly is a contradiction, because we're in the case where n is odd, but n equals 2k would mean n is even. So this is a contradiction, because n is an odd number. So this shows that this can never be fulfilled except for k equals 0, where r to the k is the identity. So this shows that no rotation, no power of r lies in the center, because it does not commute with s, and that's enough, because it would need to commute with all the elements if it would lie in the center. So we can conclude that no rotation r to the k, where k runs from 1 to n minus 1, lies in the center. What about the reflections? Maybe we have more luck here. So by this result here, all the reflections can be written like r in the form r to the k s. And again, we may assume that, no, well, that's not important, because S itself is a reflection, but we already know from this here that this does not lie in the center. Okay, so let's try this. We want to find out if this reflection here commutes with the rotation by 360 degrees divided by n. Now using this commutation relation, I can write this as r to the k r inverse s, and the right hand side simply is r to the k times 1 plus 1 times s. I can cancel the s. After cancelling r to the k as well, I end up with r inverse must be equal to r. Yeah, here this is r to the k times r. Here's r to the k, so I can cancel r to the k. I end up with this, which is equivalent to r squared being the identity. This is a contradiction, because the order of r which is clearly n, the rotation by 360 degrees divided by n, and n was supposed to be greater than or equal to 3, so it cannot be true that r squared is the identity, because then the order of r would be 2. So this shows that the center of the dihedral group of degree n, in the case where n is odd, is the identity. So all of this shows, I should write down here as well, I'm too lazy now, write down for yourself, no reflection r to the ks lies in this center here, because it does not commute with r, but it would have to commute with all the group elements. So please write that down yourself. And this shows that the center in this case, n greater than or equal to 3, n odd, the center is trivial. Only the identity lies in the center. Okay, after all this work, we're almost done. This here has nothing to do with n being odd. This is simply wrong because n is greater than or equal to 3, this argument. So we see that also in this case, no reflection can lie in the center. The same argument as here. So simply by using this, we also know in this case, no reflection can lie in the center because it does not commute with r. What about the rotations? Well, here we have no contradiction because n is even. From all this we see, this is indeed possible. So because all these were equivalences, we know that if and only if 2k is n, or k is n divided by 2, this guy here, r to the k, lies in the center. And this here is an integer because n is even, n divided by 2 is a natural number, so this is actually an element of Dn. Which element is it? It is simply the rotation by 180 degrees, because if I divide n by 2, then the angle becomes 180 degrees. This is of order 2 and indeed does commute with all... No, that's not true. That's not true. Whoops, sorry, that was too fast. So we know that r to the n divided by 2 commutes with s, but this is not enough. It has to commute with all the elements. The same argument as here, clearly it commutes with all the rotations because powers of a group element always commute because of this rule here. R to the k times r to the n over 2 is the same as r to the k plus n over 2. I can switch those around and then pull them apart. So this shows this here commutes with all the rotations. It commutes with one reflection and with all the other reflections as well. Why? Let's see. We take this and multiply it with any reflection, which looks like that. So we end up with r to the n plus k times s. What about if I switch the order around here? Then here, using this commutation relation for k equals n over 2, I can switch the order here if I put a minus sign there, but r to the n over 2 is its own inverse, because if I square it, I get the identity. So it is self-inverse, which makes sense because it's the rotation by 180 degrees. So applying it twice gives me the identity. So this means that the inverse of this element is the element itself. So I can replace this here by r to the n over 2 and then put those together to obtain the same result as here, because I can switch here in the exponent. So this shows this here commutes also with all the other reflections, and therefore it lies in the center. Okay, this is not written down perfectly, but I hope you got the idea. Okay, this is better. This here shows that it commutes with s, or I could use this argument here as well for k equals 0, so this includes this here, but I think by using this we got the idea to look at r to the n over 2. So this is also relevant for this side here. So in the case where n is even and not 2, we're in the case greater than or equal to 3, so 4, 6, 8, and so on. The center of Dn is not trivial, but contains besides the identity the rotation by 180 degrees. That's a beautiful result. If you did get that on your own and you're a beginner, you never saw that before, please leave a comment and I will congratulate you. Because I think to follow those steps is doable, but to come up with all that by yourself is for a beginner quite an achievement. Whew, all right, that's it. Very long problem set again. I'm sorry. Sorry for myself and sorry for you. Please also comment about the length and the difficulty of these exercises, if the solutions help you, and so on. Thanks for watching, and I will see you in lesson number 10. Bye bye.